Thanks, Ralph, for the introduction. And I would also like to thank the organizers. It's really nice to be here. So I think the talk is a good fit after lunch because there will not be too many formulas. And yeah, so I think just sit back and relax a bit. And you will hear about pendulum and stuff which you have heard in high school. So, okay. So I would also like to thank my collaborators. So this was a joint work with Tony Metke, Henrik Wilming, Lydia Del Rio, and Renato Renner. I've worked very closely together with Tony. So the motivation of the project is actually comes from Quantum Foundation. So we are asking if the quantum formalism is the most natural one if we would like to explain experimental data that is coming from quantum systems. And we would like to assume no prior knowledge about physics or about maths. And this question is in particular interesting because if one would find another formalism for quantum mechanics, this could probably help to overcome conceptual issues like the measurement problem. But this is really the long-term goal, and our work will just be a small step in this direction. So we were searching for some kind of unbiased brains which we could feed with data coming from quantum systems, and what we are using is actually neural networks, so artificial neural networks. And up to now, these neural networks have often been used as black box predictors. So, for example, you provide as an input image of a block tower, and then you may ask the network to predict if this tower is stable or if it will fall in the future. And these networks are pretty good in predicting this, but the problem is that it's pretty hard to understand what they have learned. So there have been different approaches focusing on extracting a physical model out from experimental data. But in these approaches, one usually assumes prior knowledge about physics. For example, one assumes that one knows the space of possible solution one is searching over. There's a famous paper where they discovered the equations of a double pendulum. But what they are doing is they search over the space of differential equation. And in addition, in these approaches, one has to assume that we already know the relevant parameters of the physical system. So this is also kind of a prior knowledge. We already know in which parameters we search the differential equations. So we somehow wanted to combine the advantages of both approaches, or at least to try it, and to find an approach that is able to find some conceptual, or that we can get some conceptual information without providing any prior knowledge. And what we came up with is a very simple model of the physical reasoning process. So our network structure will afterwards be really motivated by this process. And since it's motivated by the reasoning process and not by a specific physical system, actually it will be applicable to a lot of different physical, data coming from very different physical systems. So this model is very simple. So we start from observation. You may think of the time series of a particle moving with constant velocity, starting at the initial position x0. And now we would like to encode this information into a simple representation. So a physicist would just store the initial position and the velocity in this representation. And afterwards, we can ask a question. So we could, for example, input time in the future as a question. And what we would like to do then is we would like to predict the answer of this question, right? And so I said that we would like to find a simple representation of the physical system. So to search for simple representation, we have to formalize what we understand to be simple. And we formalize this just by requiring the following properties. So we would like the representation to be sufficient, meaning that we just have enough information in the representation to reply to all possible questions that may be asked. So you may think of a fixed set of possible questions that can be asked. Then we would like to be the parameters stored in the representation to be independent, meaning that the information stored in one parameter should not provide any information about the other parameters. And so, okay, we state this more mathematical in the full technical version, but I think it's pretty clear what we mean here. And the last property is just that we would like this representation to be compact. So we would like to have the minimal number of parameters. And okay, so as said, we will implement this with the neural network structure. So let me first quickly recall what how these neural networks are built. So they are built up in neurons. So a neuron is just a function which takes some real numbers as input, and then we sum them and multiply them with some weights wi, and we add a bias b. This is just a real number, and then we apply activation function to this term. And there are different choices of activation function. We have chosen this ELU activation function, which is essentially constant if the input is small, and then starting from a certain threshold, it starts to go linear in the input. And okay, the output of the neuron is then just this real number, which is called activation. And neural networks are now built of such neurons, so we put them into layers. We have an input layer, output layer, and in this example, one hidden layer. You can clearly add more hidden layer if you would like to. Then it's called deep neural network. And so, okay, the input neurons are kind of special because we don't sum anything here, calculate this activation, but we just take the input and forward it to all neurons in the hidden layer. And then these hidden neurons here are all of this kind, so they calculate the activation, and then they forward the activation to all neurons in the next layer, and we get a certain outcome. And the thing you have to know about these networks for the following talk is just that if you choose enough neurons, then there's a proof that you can approximate any continuous function arbitrarily well. So meaning that you can always choose the biases and the weights, which are the free parameters of this neural network, such that you can implement these functions. Okay, so now it's really straightforward to implement this physical reasoning process with neural networks, because we just implement the encoder and the decoder function with such neural networks. And okay, so right, then the whole function is just a function which takes observation in a set O, questions in a set Q, and should provide the answer A. And as explained here, we split this function into this encoder and decoder. And okay, the names encoder and decoder, they actually come from machine learning, because this is a very famous structure in machine learning. If we leave away this question input, then it's exactly the structure of a so-called autoencoder. And also motivated by machine learning, we call this layer here, where we store the representation, latent representation. Okay, so how does now the training work? So we have this encoder and decoder, which we can think of just parametric family of function, right? Where the parameters are these weights and biases of the networks. And we would like to find the right choices of these biases and weights such that the encoder and decoder will finally perform well, meaning that we have good prediction accuracy and that we find a simple representation. So during the training of this network, we just provide examples. So we provide such triples of an observation, a question, and the correct reply. And then during the training, we adapt these parameters such that, as said, the prediction accuracy is optimized, and we are searching for minimal uncorrelated representations. And searching for this minimal uncorrelated representation is actually quite a hard task, and there's a lot of research going on in machine learning, and we have used this recent paper here about beta variational autoencoders to actually be able to train it. But I will not go into the technical details how this works. But it's enough for the talk. It's enough just to think of this a method such that we can learn these representations. Okay. So now I will demonstrate the working of this network on 4 different examples. Actually, 3 examples will be classical and 1 will be quantum. So the first is a very simple example from classical physics. So we just consider a damped pendulum where we have a spring constant kappa, a damping factor b, and we think of a fixed mass m. So here you can see an example of such a time evolution and also of the predicted one of our network structure. I will just explain how we trained it. But actually, it's not, the prediction will not be the interesting thing, but the more interesting thing will be which representation was learned actually to be able to predict well. And okay, so what we do during training is that we sample, we have different samples, and we sample the spring constant and damping factor independently. And then for these samples, we just create the time series of the damped pendulum, and as an observation, we just provide a short time series. So I think we have about 10 time steps, and we put this into as an input here, as an observation input to the network. And then the question in this example is just a time in the future at which the network should predict the position. And now the interesting thing that we find is the representation. So here you can see 3 latent neurons, and we plot the activation of these neurons, which you can think of the stored parameter in the representation, against the damping factor and the spring constant. And you can see that, okay, the first neuron depends only on the damping factor and is nearly constant in the spring, constant, where the second neuron does actually just store the spring constant, and the third one is set nearly constantly to 0, telling us that actually 2 degrees of freedom are enough here to store. Okay, so somehow this formalization of this reasoning process leads to the same parameters that we would store as physicists in this system. And as a second example, we wanted to see if we can learn also more complicated encoding, so to see if this network structure, which we call SciNet just for simplicity, if this SciNet can also learn conserved quantities. And what we are considering here are just 2 particles. One is fixed on a stick and is rotating around the origin, and then it collides with a freely moving particle at the y-axis. And so since we have the only external force, right, is acting on the origin, so we have angular momentum conservation, which is written down here. And we will, for the training of the network, we will sample from different such collision experiments where we choose the initial position and velocity different in each sample. So what we provide as an observation input are just a time series of both of the particles before the collision, and as a question input we provide the time series of the free particle after the collision together with a time t prediction at which we would like to predict the position of the rotating particle. So clearly physicists would just calculate the total angular momentum before the collision, and afterwards we can use it to calculate the position of the rotating particle given the velocity of the free particle. And what we find again is that this SciNet can also recover this. So if we plot the latent activation of one latent neuron against the total angular momentum, we can again see that it's a monotonic function in it. And it can, you see, sometimes, okay, there are several points if we cut like this, but this just means we have several scenarios which have clearly have the same angular momentum, and okay, it learns to map them to the same point, right? Okay, now finally we have also considered a quantum example. So in this example we just considered tomography of 1 and 2 qubits, and we will see that we can find a representation of pure states of 1 and 2 qubits. And in the full version, we also show that one can use this network structure to decide if a set of measurements is tomographically complete or incomplete. But I will not talk about this here. So in this example, we were very careful to choose the data such that the person in the lab would not need any knowledge about quantum physics to actually collect the data. So you can think just of a person in the lab. He has 2 devices. One device is able to prepare quantum states and pure states, and he has just some buttons and tiles that he can choose, and he assumes if his setting is the same, that the same state is produced. And then he has a second device, which is a measurement device, and here we assume that he can just perform binary projective measurements, meaning that we have two outcomes, 0 or 1, dependent if you have projected on the considered state or not. So we have these measurements alpha, these binary projective measurements, and project on a state psi, and the model is just the Born rule, so the probability that we get outcome 0 for state psi and measurement alpha is just the projection squared. Okay, and so what we provide as an input now to the network is that we just choose randomly measurements, and then we perform this measurement several times on the same state. Then we get out frequencies, so we can estimate the probabilities to get certain outcome and for a certain measurement on a given state psi, and then we provide these probabilities as an input to the network. And as a question, we just provide a parameterization of the measurement, just so you could think of just providing the parameters that you, the dials and the buttons that you see on your measurement device, and you provide this as a measurement. And so for measurement omega, we would then like that the network predicts the probability of measuring omega given the state psi. And so, okay, again, we find pretty good prediction accuracy, but we are again more interested in the representation. So what we did here is we trained this network with data coming from 1 qubit and from 2 qubit, and for a different number of latent neurons. So here you see the prediction error, and here the number of latent neurons. And you see that actually 2 latent neurons are required to achieve pretty good prediction accuracy. So this tells us that, okay, pure quantum state on 1 qubit is actually described by 2 real parameters, which is clearly right. I mean, thinking of the 2 angles of the Bloch sphere. And on 2 qubits, we find that actually 6 parameters are required, which is again correct. I mean, we have 4 complex parameters, 8 real ones, and then we are only interested up to global phase and we have normalization, so we have 6 left. And okay, so small remark here, you may notice that there's still a significant change going from 2 to 3 and 6 to 7. This is actually due to a technical issue with neural networks, because in this case, the encoder should learn a discontinuous function. You may think of the Bloch sphere in the 1 qubit case, and then you would like to map the points on the sphere to the angles theta and phi. And I mean, the angles are cyclic, so you have, at a certain point, you will have a cut in this function. And these networks are not very good right in approximating this continuous function, so they will just be very steep there, and okay, the prediction will not be very good there. Okay, but yeah, we go into detail about this problem in the full version, if you are interested. So let me come to the last example, which is again a classical example. And in this last example, we actually extended the decoder a bit, such that it is able to evolve the representation in time. So actually, the reason why we do this is that we can search for representation that allow for simple time evolution. So you may think of this as adding an additional property on the representation to be simple. So the structure is now the following. We have observation, we encode it into a representation at a certain time t0, then we evolve it for a short time and to a representation at the time t1, and then we decode it to provide a certain answer. So in our example, we don't have a question input here because we always ask the same question, but clearly you could add one if you would like to. And then again, we have a small time evolution, we decode, and then we do this recursively. So this is also a very well-known structure in machine learning. It's called a recurrent neural network. So note that the network for the time evolution is always the same, and also the network for the decoder is always the same in this structure. And so the data that we consider here is the data that was collected by, simulated data of the one that was collected by Copernicus in the 15th century. So we use so we consider Earth, Sun, and Mars, and then we collect a time series of the angles between a fixed star background and the Mars, and the fixed star background and the Sun. And what we are wondering is if we are just given this time series, is SciNet somehow able to recover that it should actually use the representation as seen from the sun, so the angles as seen from the sun, because clearly they allow for a very simple time evolution. And so what we provide as an input is just an observation, so it's just the angles at a certain time t0, and during the training we will vary this time t0. And as said, the question is implicit, so we always ask the same question, and the question is just to predict the angles as seen from the Earth at a specific time ti. And okay, and then so the representation that we find is the following. So we plot the two activations of the latent neurons against the angles as seen from the sun, and as you can see, they are linear in this angles. So note that we could not expect that they perfectly separate the angles, because any linear combination of the angles as seen from the sun actually still evolves linearly in time. So there was no reason to separate them. Okay, yes, so I mean, you can conclude from this. Yeah, I leave it to you what you want to conclude from this, but I think, okay, somehow, yes, at least this network can find this representation and could maybe, if we wouldn't know it before, it could probably help us to give a hint which representation we should use. Okay, so to conclude, Ralph, was I too quick, or did? 8 minutes, okay, good. So to conclude, I don't think the particular examples are very interesting, but I think this direction could be interesting, that we introduce this network structure that is motivated by the physical reasoning process, and it's not a network structure that is motivated by a specific physical system. And this actually allowed us to apply it to data coming from very different systems. And as we have seen, somehow this network structure finds the relevant degrees of freedom that are required to reply to all possible questions that may be asked. And so this was not completely clear to me at the beginning of the project. I mean, one could ask, yeah, just looking at damped pendulum, is it clear that we should work with the frequency and the damping factor, having no knowledge about maths or physics? And so somehow, yeah, this work formalizes this in a certain sense, such that we find, oh, actually, yes, there's a reason, and we find exactly these parameters if we formalize it like in this setting. And okay, the last point is, I think that it could be interesting for machine learning to use this question input also for different systems, because usually they use this autoencoder structure, and then they have to save all the information of the input in this latent representation. But if you have this question input, right, then you only have to save the information in which you are interested. So, and yes, okay, there was also a recent paper about this, where they used this structure for some movie rendering stuff. So very different application, but okay. And so for future work, I think one possible concrete direction which could be interesting is to search for spatial representation of quantum states. So one could add some additional properties and, for example, search for representation of several qubits that separate the local and non-local degrees of freedom. So for 2 qubits, such a representation is known analytically, but it gets pretty difficult to find them afterwards. And I think it already took quite some time to find it for 2 qubits. And another direction, which is a bit less concrete, is that we would like to put this network into an environment, and such that it can learn itself which data it should collect to find a nice representation. Because at the moment we have still prior knowledge we still use prior knowledge in the structuring of the data that we provide to the network. And okay, as said in the beginning, the very long-term goal would be to somehow extract conceptually new information from from just experimental data. But this is really the long-term goal. Okay, so all of our code is open source and it's also documented. So if you would like to try it, please feel free. You can also find the link in our archive version. And so I would like to thank again my collaborators. And yes, here you have also the archive link. Thanks.
Thanks, Raban. Any questions?
I'm just wondering whether these representation that you found for qubits or for quantum states, really, could you think those as dimension witness for the system?
Yes, I'm not familiar with what dimensional witness means, but if it just means the number of degrees of freedom in the system, then yes, is this the same? I mean, it's really, so we formalized this mathematically what actually is captured by this number of latent neurons, but it's actually really, so if you think of the input data coming from is sampled on a manifold, then you really find somehow the dimension of the manifold. And yes, so I guess this is probably equivalent.
Hi, thanks for the talk. So at the beginning you said that somehow one of the motivations was to double check somehow that we haven't come up with sort of some path dependent theory, and now we're in conceptual muddles that we can't free ourselves of and stuff, and that we might be able to come up with a better version of quantum theory or some other theory using these kinds of tools. And I was wondering, I mean, it's a bit of a crackpot question, but couldn't you apply the same just to, say, the scientific method itself or the physical reasoning process itself? So you say, I mean, obviously you run into some kind of infinite regress of meta criterions, but in theory you could say, here's an architecture, and that thing now somehow we check what kind of reasoning process that architecture thinks is a good reasoning process to make sense of data. I don't know, it's probably more not really a question to you, but have you thought about these things, or is there some obvious problem, or do you get my point? Or?
Okay, I mean, at the moment thanks for the question. I mean, at the moment we can just somehow find these relevant degrees of freedom, right, with respect to questions. So probably one would really have to pin down this question and make it very concrete to ask. But in the very long-term goal, it could go in such a direction, maybe. But at the moment, I think it's quite unclear what one could do. So we haven't thought about this yet.
So when you make the question, and let's say you change it, do you have to train the decoder part again?
So if you just so the question are just real numbers, right? So if you just change this number bit and it's kind of a range where we trained it, then clearly you don't have to retrain it. But if you now completely change the question and ask something different, then you have to retrain the decoder. I mean, if the representation is still sufficient for the new question, then you have to only retrain the decoder and you can use the same encoder. But if not, you have to retrain the whole thing.
So, for instance, if you, instead of asking for the time, you ask, okay, give me the time when the particle is at this position. Can you do this kind of things?
Then you have to retrain. I mean, you could use the same encoder here because you have all the information, but you have to retrain the decoder. Yes, it cannot directly reply to this. Yes.
So it seems to work very well, and I'm wondering whether that's because, so in machine learning and deep neural networks, you typically go from a function in Rm to Rn, or whichever one is smaller. And the dimensionality of the kind of polynomial that represents your answer, is it just very low? Is that the reason why it works so well? Because usually you have problems with overfitting and stuff like this, which occurs when the relationships between the data are very complicated and very high order.
Yes, I mean, clearly, yes. I mean, if the dimension of the input data would be very high, yes, then this would not work, right? Also, it gets more and more difficult to find the independent parameters. Also, if the bigger the representation gets, yes.
I think we might leave the rest of the questions later because we've come to half an hour. So let's thank Raban again.